In this lesson, we're going to be investigating the Bronsted-Lowry theory of acids and bases. According to the Bronsted-Lowry theory, an acid is a proton donor in any solution, whereas a base is a proton acceptor in any solution. Acids and bases occur in conjugate pairs. So, if we look at hydrochloric acid reacting with water to form hydronium, H3O+, and chloride ions, Cl-, we can see that the HCl donates a proton to the water to make water H3O+, and as a result, having donated its H, it now only has Cl-. So because it donated a proton, it is the Bronsted-Lowry acid. Water, having accepted the proton, is called a Bronsted-Lowry base. That might not make a lot of sense to you because you might be thinking, well, water is neutral. Well, again, anything by this definition that accepts a proton is considered to be a base. Now, once water has accepted a proton, it becomes H3O+, which is called the conjugate acid, because if we look in the reverse direction of the equilibrium, H3O+ could donate an proton to the Cl- and form HCl. Right? So if we look at the reverse reaction, H3O+ is the acid, and Cl- would be considered the conjugate base. In this example, NH3 with water forming ammonium and hydroxide, NH3 is going to be your Bronsted-Lowry base, and water is actually going to act like your Bronsted-Lowry acid because water will donate its proton to ammonia that will accept it. And if we look on the reverse side, well, now that ammonia has an extra hydrogen to become ammonium, since it has that extra hydrogen, it could go backwards and redonate that proton, so it could become a proton donor, and OH- becomes the conjugate base. So with Bronsted-Lowry, we talk about acid and base, or conjugate acid and base pairs. Well, as you can see here, the acid becomes the conjugate base, and the base becomes the conjugate acid. Same thing here. The base, after accepting the proton, becomes a conjugate acid, and the acid, having donated the proton on the other side, is a conjugate base. So our little note that we're going to put here is acids form conjugate bases, whereas bases form conjugate acids. So write the conjugate acid of HPO4 2-. So the conjugate acid would be after it has donated, once it has accepted a proton, it can become, so we show it having accepted another proton, it can then further donate a proton after it's accepted it. So if we look at here, the conjugate acid, we have to add a proton to that, and so that becomes CH3 NH3 positive, and I know that the H has to go on here because if the H joined over here, then you would have CH4, and that could not bond to the NH2. And then the conjugate acid is, with a proton, so that would be HBr. The conjugate base is minus a proton, so that would be C6H5COO negative. This would be CO3 2 minus, and that would be NO2 minus. Those are the conjugate bases of these acids. So the stronger an acid is, the weaker its conjugate base. The same is true for the opposite. Weak acids equal stronger conjugate bases. Okay, so for example, if you have a strong bond between the H, the hydrogen, and its conjugate base, A minus, if that is strong, okay, so if this is right here, that's a strong covalent bond. Then, strong covalent bond. So then that means that the HA acid will not donate H plus because it is strongly bonded to A minus. So as a result, if you have a strong bond between H plus and A minus, you have what's called a weaker acid or a weak acid. However, if you look at its conjugate base, A minus or A negative has a strong attraction to H plus, as seen by that strong bond, right? So if A minus has a strong attraction to H plus, then that means that A minus is a stronger proton acceptor. So it becomes what we call a stronger base. So, stronger base. Weak acids make stronger bases because of that strong covalent bond. A minus has that strong attraction to H plus, so H plus will not be given up easily. And if A minus is by itself and an H plus is nearby, well, it's really going to accept that H plus because it has a strong attraction. So that makes it a very stronger or much stronger base. If you have a weak bond between H and A, if that is a weak bond, then that means that the HA acid will donate H plus easily because of the weak bond. And so that would make, if you have a weak bond between H plus and A minus, that makes it a strong acid. Okay. Whereas if you have an A minus and it's weakly bonded to H plus, that means that A minus has a weak attraction to H plus. Has a weak attraction, so it's not very strongly bonded to the H plus. So that means if it has a weak attraction, A minus is a weak proton acceptor. If it is a weak proton acceptor, that makes it a weaker base. A weak base. An amphoteric or amphiprotic substance is a substance that can act as either an acid or a base depending on what they are reacting with. So if we take a look at here, HCO3 is amphoteric or amphiprotic because if it reacts with hydrochloric acid, it will accept a proton to become H2CO3. Whereas if HCO3 reacts with a base, it will donate its proton. So it can basically go either way depending on what it is reacting with, right? So it could either be an acid or a base depending on what it is reacting with, just as it says up here. And here's some of the other examples, like water is an example of that, or hydrogen phosphate ion is an example of that as well. So neutralization. It involves two substances, and you must initially determine whether they are weak or strong acids or / bases. Okay. And so what you have to do here is you have to take a look. Well, HNO2, that's going to donate a proton to the cyanide ion. So this is the acid, and this is the base. NO2 minus then becomes your conjugate base, right? After HNO2 has donated its proton, it becomes the conjugate base, whereas CN minus becomes HCN, and so therefore it is the conjugate acid. So the two acids here, so HNO2 and HCN, are in competition to donate protons. So the question is, will this donate protons to CN minus, or is the reverse reaction, right, this one right here, which reaction is going to happen more, the forward reaction or the reverse reaction? Same thing can be said for the bases. The two bases are in competition to accept protons. Okay. The stronger base succeeds to a greater extent, right? So if this is a stronger base, then the forward reaction would happen more because this species will accept protons more than this species will, right? So what happens is the strong acid, the stronger acid and the stronger base succeed in destroying themselves. And what that means is that basically that reaction will happen more. Okay. So the equilibrium favors the side with the weaker acid and weaker base. Sorry, let's just put weaker here. Weaker acid and weaker base. So how do we know which one is the stronger acid and which one is the stronger base? Well, we have to look at the Ka values. HNO2 versus HCN. And so we're going to quickly look up those Ka values in our chart. For HNO2, it's 7.2 times 10 to the negative 4. And different tables may have different values, so there might be some difference between the values that you see. Whereas HCN is 6.2 times 10 to the negative 10, so 6.2. Again, there might be some discrepancies in the values that you see on different tables because these are experimentally determined, so different tables may have different values. As we can see here, the HNO2 has the stronger Ka value, so that means that this will succeed in donating its proton more so than the conjugate acid will. So the forward reaction is happening more, which means that you will have more products. So the equilibrium favors the side with the weaker acid and base. So if we looked at equilibrium, we would see more NO2 minus species and HCN minus species because the stronger acid and the stronger base end up reacting quite a bit to produce these two species on the right-hand side. And then you can basically take a look over here. It says predict which side of the equilibrium would be favored in the reaction between hydrosulfuric acid and the fluoride ion. So if we did this, H2S, this is hydrosulfuric acid plus the fluoride ion. Okay, we have a arrow here, and then we get HS minus, which is aqueous, and HF, which is aqueous. So what we need to do is we need to check the Ka values for H2S and for HF. And so whichever has the higher Ka value means that that side would be favored in, or rather, that species would react more. So we can just quickly take a look at our tables. So when consulting our tables, we see that HF has the higher Ka value, which means that this is going to very much succeed in donating its proton to HS minus, so the reverse reaction is going to happen more. So the left side of the equilibrium would be favored. So left side would be favored. Okay, and so if you complete these questions right here, questions 1 to 11 on page 4 of your note package. Thanks for watching.